Okay, so welcome everyone to the lecture series on electromagnetic waves. So today we'll start with an additional topic, part B. So today we'll try to cover a polarization in dielectric medium or material. So we know that the dielectric material differs from conducting material in that in the dielectric material, ideally there is no free charge that can be transported within them to produce a conduction current. Okay, as we know that in conductors we have really an abundant number of free electrons. Okay, which are really responsible for the conduction of a current. Okay, but we don't have any free electrons. Ideally speaking, no free electrons, but practically speaking they are very small in the numbers. Inst Instead, in the dielectrics we found that all charges is confined to the molecular or lattice sites by the Coulomb's forces. Okay, all these charges are confined to this particular molecules. So the question is, what happens when I apply an electric field? An applied electric field has the effect of displacing the charge slightly, okay, leading to a formation of n assembles of electric dipoles. Okay. Yeah. Now, what happens is because of this particular thing. Okay. So, as we have discussed this particular thing last time. Okay. There is a small displacement from this. We could say a nucleus. Okay. Um, and you have a free electron. Okay, when you try to apply an electric field, okay, to this, you will try to see it forms a kind of a dipole as what we have shown here, like this. Okay, there is there is a small displacement. Okay, because of this an applied electric field. Okay. So that's what we try to say that an applied electric field has an effect of displacing the charges slightly, okay, which leading to a formation of an n assemble, formation of n assembles of electric dipoles. Okay. Now we say that there are two types of dielectric. Okay, the first one is called as polar dielectrics. Okay, which are dielectrics that have permanent electric dipole movement. Okay, so yesterday we have discussed about this, what you mean by dipole movement. Dipole movement is you have a positive charge and we have a negative charge. Okay, and they are separated by a very small distance. Okay, an example of dielectric of this kind of material that is having a permanent electric dipoles as example of water. Okay, that is what is shown in this particular figure. Okay, now what we could say that as depicted in this above figure, you could say A or 5.41, the orientation of polar molecules is random in the absence of an external electric field. Okay, so these dipole moments are oriented very random. Okay, when an external electric field, this is in absence of electric field E naught. Okay, in presence of an electric field, okay, a torque is set up such that it causes molecules to align with an E naught. Okay, so you could see that they try to align, okay, align themselves, okay, slightly. Okay, it's not that perfect alignment. These were very randomly oriented. These were randomly oriented. Okay, and when you apply an electric field, they try to align, okay, align with an E naught. However, the alignment is not complete. Okay, due to a random thermal motion, the aligned molecules then generate an electric field that is opposite to the applied field but smaller in the magnitude. Okay, so So what you could see now they have got an perfect alignment. Okay, so you could say that now they have kind of a net dipole moment. Okay, they have some net dipole moment. Initially here the net dipole moment was 0. Okay, you could say the net dipole moment was 0 here. Now they have some net dipole moment and they have an electric field. And the electric field, as we know that it will be from positive to negative. Okay, I say it is produced by this polarized material. Okay, and it is in the opposite to this one. Okay, yeah, but it will be the smaller in the magnetic. The second type of material is called as non-polar dielectric, okay, which are dielectric that do not possesses a permanent electric dipole moment. Okay, they don't have any permanent dipole moment as what we see some material have it. Okay, non-polar dielectric material in an external applied electric field can induce a dipole moment, as what we have tried to show that initially it does not have any dipole, but when you apply an electric field to that particular non-polar material, it induces an what we say is it induces and the dipole moment. Okay, and you could see that it really tried to produces an electric field due to this polarization. Okay, and you also have an applied electric field, and difference of them, you have a net electric field inside the dielectric field. Okay, that's what now what you could see that what we have said here is, okay, now you can really treat this particular figure as, okay, you could say that you have induced surface charges on the spaces produce an electric field EP. Okay, so I'm taking a case where you have a material, when you apply an electric field it induces an dipole. Okay, and you could see these dipoles are uniform. Okay, all of them have aligned in the same direction. Okay, all of them have aligned in the same direction. So what I could say that there is some cancellation interior, this plus and this minus, this plus and this minus. As a net effect, what I can see is you have a negative charge at this side of the surface and you have the positive charge at this side of the surface. Okay, yeah, and this particular thing produces an electric field which I'm going to call it as EP. Okay, and and hence what we could see that the EP direction is opposite to E naught and leading to E equal to E naught plus EP, and this E which is inside the dielectric is actually less than the E naught which is applied in the outside the dielectric material. Okay, now what this short thing will, what with this short discussion, what we are trying to gain is that when you apply an electric field to dielectric material, okay, inside the dielectric material you have an electric field. Okay, you have an electric field. This is exactly an opposite to a conductor. Okay, so where we said that when you take a conductor, okay, and if you try to apply an electric field to that, okay, we say that inside a conductor the electric field is 0. Okay, I hope you remember we have discussed this particular thing. Okay, inside the electric field, I mean inside the conductor the electric field is 0. Okay, but that's not the case in the dielectric. Okay, in dielectric material, okay, there is a formation, I mean what we say is there's a formation of dipoles. Okay, or we could say dipole movement, and that is called as a polarization. Okay, this particular phenomena is called as polarization, and because of that there is a dipole movement, and those dipole moment produces some field, okay, which is opposite to an applied field, and as a net, you have an electric field inside the dielectric material, which is really less than the outside one. Okay. Yeah. So this is what we got on a rough point. Okay. Um, Now the thing is, we need some. We need some proper relationship. Okay, because I was having a relationship between D and E in the free space, as I said, to epsilon naught times the E. Okay, epsilon naught is a permittivity of a free space. Okay. Now the question is, how do we really compute the electric field inside the dielectric material, and what is the relationship between D and E inside the dielectric material? Okay, so in order to derive this relationship, let us go with this small discussion. Say that if there are n dipoles, per unit volume, okay, and so what I'm telling is inside a unit volume, okay, 1 unit volume, you have n number of dipoles, n number of dipoles within. So now within delta V, okay, within a delta V volume, there will be n into delta V dipoles, and the total dipole moment is obtained by the vector sum. Okay. So you can add all the dipole moments inside this delta V volume. Okay, delta V volume, delta V total dipole moment. Okay, so now we define a new term. Okay, which is really convenient to work at a microscopic level. Okay. See, we cannot really do this exercise that, inside a dielectric material, there are, there are really a large number of atoms, okay, and finding an, what you could say, that is electric field due to such each dipoles, and then find what is this EP, okay. Instead of that, what we'll try to do is, we'll try to define a new quantity calling as a polarization. Okay, this is denoted by a capital P. Okay, if you remember dipole moment, we represent by saying P, which we denote with a small p, which is Q times D. Okay, if you have positive charge and negative charge, D is the direction. It's a vector from negative charge to positive charge. This is plus Q and this is minus Q. P is Q times D. Okay, whereas we define one more term called polarization, okay, which is capital P, as a dipole moment per unit volume. Okay, so we define uh, dipole moment per unit volume as the polarization. So this is, we know that it's a total dipole moment inside this delta volume, delta V volume. You divide it by delta V, you get the dipole moment per unit volume, and uh, we want to see it for see it for a small volume, as small as possible. So limit as delta V tends to 0. So the polarization unit is coulomb per meter square, and you should know that the unit of dipole moment is coulomb meter. Okay, is coulomb meter, whereas the polarization is coulomb per meter square. Okay, yeah. So so once we got this term, that is polarization, dipole moment, now let us try to calculate the potential field. Okay, let us calculate the field. It is a potential field due to this polarized dielectric. Okay, so you have a dielectric material, you apply an electric field to that. We know that it gets polarized. When I say it gets polarized, it means that there is an induced there is an induced dipole moment, or if they are a polar molecules, okay, type of dielectric material, then we find that those polar molecules try to align themselves in a proper direction, and then we say that material is yet polarized. So for this polarized dielectric material, let us try to find a potential field. Okay, consider dielectric material shown in below figure. Let it consist of dipoles. Okay, with dipole moment per unit volume as P. Okay, so with dipole per unit volume as P. We know that the potential due to a single dipole moment, okay, is given by P dot AR hat divided by 4 pi epsilon R square. Okay. Now the potential dV. So here I have taken a complete dielectric material, and inside that dielectric material we have taken a very small volume dV prime. Okay, and here outside this dielectric material at a point O, we need to find the potential field due to this polarized dielectric material. So first we'll try to find what is the potential due to this tiny volume, tiny volume polarized material, and then we'll integrate to find the total, then we'll integrate to find the potential field due to this complete polarized dielectric material. The potential dV at an external point O due to an dipole moment P dV prime, okay, is given by PdV dot AR hat. Okay, dV is something you can write it. It's actually PdV prime. Okay, due to a dipole moment. Okay, dV P into dV prime. Okay, so P is actually, you could say it's uh, as we said, it is per unit volume. Okay, dipole moment per unit volume. Okay, and you multiply with the volume, you will get it is like a dipole. So which is, we can write it as AR hat divided by 4 pi epsilon R square, which I can write this as P dot AR hat dV prime divided by 4 pi epsilon R square. Okay, now what we are trying to tell is, let us transform this equation to in a most convenient way, okay, which will facilitate for the physical interpretation. Okay, now in order to do that, what we say that the gradient of 1 by r, okay, we know that the gradient of 1 by r is AR hat by AR hat by r square. This is quite simple, you can really check it out. Okay, so which means that this particular term I can write it as gradient of 1 by r. Next we have a vector identities, that is, which is also called as the product rule. Okay, that is this gradient, here we have the divergence. Okay, and it's a divergence of two functions. A is a vector and f is a scalar function. That's what we call as a product rule. Okay, so we know del dot is a divergence. Okay, it's a divergence of two functions. It's a product rule. It says that it's a divergence of these two divergence of f into a is f times divergence of a plus a dot, okay, a dot del f. Okay, so in our case you can try to if you try to see this right hand side, okay, and this term, okay, you could see that we have this term which is really same as this term. Okay, so which means that the P is same like an A and F is same like 1 by R. Okay, so I have just recalled a vector identity, and in a vector identity the right hand side, okay, the last term is same as this term which we have here. Okay, So we know that it means that this term I can write it as del prime fa minus f del prime a. Okay. Okay, that is this, and this is same as this one. Okay, so just I can replace those names, which is 1 by r p, okay, minus 1 by r del dot p. Okay, so that's what we have written here. Okay, so this is same as this. So what we can write now, p dot by r square as del dot p by r minus del dot p by r. Okay, now substituting this thing, okay, equation 6, this part, in equation 2, okay, and integrating over the entire volume B prime of dielectric. Okay, so this P dot AR by R square, okay, I can write it as this term. Okay, so and I'll try to integrate over the throughout the volume. Okay, so that I'll get the complete potential field due to this polarized dielectric material. Okay, now applying divergence theorem to the first term. Okay, and you should recall divergence theorems is it tries to convert the surface integral to the volume integral, or volume integral to the surface integral, del dot d dv. So here I have, that's what define divergence theorem to the first term. Okay, so I have something del dot. I can write it as a surface integral. Okay, it's a del dot of what, p by r. Okay, so I can write it as surface integral of p by r, okay, dot ds. That's, you could see that I applied a surface integral p dot ds, and ds I have written like ds into a hat divided by 4 pi epsilon r. That's a surface integral, and this term we have kept as it is. It's a volume integral of this term. Okay, so now we have some nice physical interpretation for this. Okay, now what does it really mean that? Okay, before that, a n hat is an outward unit vector normal to the surface S of the dielectric. Okay, now comparing the two terms of the equation 8 with below equation. Okay, so we know that we know what is the potential field due to the surface charge, and we know what is the potential field to the volume charge densities. This we have discussed. We know that is given by V equal to 1 by 4 pi epsilon. Okay, rho s into ds divided by r. Okay, because there it falls as 1 by r. Potential falls as 1 by r. And it's the same 1 by 4 pi epsilon rho v dv 1 by r. Okay, yeah, and these are they have written in terms of the position vector. You could see that if we compare this and with this, what we really come to know that, okay, the two terms of equation denote the potential due to the surface and volume charge distribution with the densities rho ps is equal to p dot a n hat. Okay, you could see that they really resembles. I can write rho is equal to p dot a n hat, and here rho v equal to minus del dot p. Okay, now, yeah, so what does it mean that the potential field, okay, due to the dielectric material is due to the two charge distribution. Okay, one is surface distribution, one more is the volume distribution. Okay, I should write it as actually as PS. Okay, I'll tell you why this is PS. Okay, and why this is PB. We don't write it as rho s, but we write it as PS. Okay, or some author write it as B into S. Okay, bound charge densities. The more appropriate to say is, okay, So what this particular equation 8 is trying to tell that we have a potential outside dielectric material due to the two bound charge densities. One is bound surface charge densities and one more is bound volume charge density. Now why this is bound? Okay, from our discussion we can say that where polarization occurs, okay, that is where polarization occurs, it means polarized electric material inside a polarized electric material, an equivalent volume density rho pb is formed throughout the dielectric, while an equivalent surface charge density is formed over the surface of the dielectric, where rho ps and rho pv are referred as bound or polarization surface and volume charge densities. Now we need to little understand what we mean by bound charge densities. They are distinct from free charge density. So this particular thing is really very important to understand. Okay, bound charges are those that are not free to move within a dielectric material. Okay, they are actually not bound. Okay, so now what we are seeing, the surface charge densities and volume charge densities inside this material is because of effect of polarization. Okay, as I told in the very first part, okay, when there is a polarization happen inside the dielectric material, so you can think there is a cancellation and you could see as a net effect, okay, you have a negative surface charge density and positive charge density. Okay, this is a case where you have uniform dipole orientation. Okay, yeah, and these charges are actually not free to move as they are in the conductor case. Okay, they are called as bound charges. Okay, so here I was. Yeah, they are not free to move within an electric material. They are caused by the displacement that occur on molecular scale during polarization. Free charges are those that are capable of moving over a microscopic distance as electrons in the conductors do. Okay. Yeah. Now let us try to understand this particular whole thing. What I'm trying to tell you is here. So say here you have a cylindrical material, dielectric material, and say that you have an applied electric field, and say that uh, uh, there is a formation of dipole movements, and you could see that all these dipole movements have aligned in the same direction. That's what we could say that. We say it's an uniform dipole distribution. Okay. Now, what we could draw an equivalent picture for this is, you could see that there is a cancellation of positive, negative, positive, negative, positive, negative, and in the upper side of the face, okay, I can say that you have a net positive charge density, and as the cancellation also happens here, 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 and in the bottom, you have the net negative charge. Okay, plus qp and minus p. This p and again indicates a polarization or the bound charges. Okay, and this try to produce an electric field which we call it as an ep. Okay, yeah, if inside a material, okay, if there is an uniform dipole distribution, then you could see that you don't have this volume charge densities. Okay, as we said that there is a formation, that's what we say in this statement. Okay, polarization occurs, an equivalent volume charge density formed throughout the dielectric and equivalent surface charge density is formed. Okay, but in the case of when there is a formation and uniform dipole, okay, this particular rho pb will be 0. Okay, whereas in some other case it's not possible to have an uniform dipole distribution. In that case you have both the things, that is both surface charge density and the volume charge density, bound volume charge and bound surface. As an example, what I have shown here, non-uniform dipole distribution. I have not shown like in the 2-dimensional, but in the one-dimensional scale I have shown. Okay, say this is, you have an inside the dielectric material. Okay, so you could say that at the lower side you have this dipole moment with this thing, and here you have this dipole minus q plus q, and middle you have this one, and you could see there's cancellation. I mean, this addition of that leads to like minus 0.2 q, and here it leads to a 0.4 q, minus 0.8 and minus q. So at the surface I have minus q here, at this surface I have 0.8. But inside this volume, you could say that I have something 0.2 q as a charge density something. Okay, this is just to visualize. Okay. So now what is the whole picture we are trying to see? Okay, so what we are trying to see is when you take a dielectric material, okay, when you apply electric field, it undergoes a polarization, and we can see this polarization as a surface charge, bound surface charge densities, okay, and the volume charge densities. And in the case of a uniform distribution, the volume charge density will be 0, otherwise it do exist. Okay, so and here we have that particular potential field. Okay, that's what we have, the potential field due to those bound charge densities. Okay. Okay, so this is something very interesting. I mean, we started to find then a potential due to a dipole moment, and we end up in expression having I mean, that is a potential due to and charge densities, that is volume, I mean, that is bound charge densities. Okay, yeah. So once we got this picture with us, okay, so what we can say further is the total positive bound charge on the surface S, okay, bounding to dielectric, okay, they are not free to move, still they are bound to dielectric, is okay, just you can make the surface integral of P dot ds, okay, and we know that the I mean, we can write this as in terms of charge density, that is rho ps ds. Okay, while the charge that remains inside the surface is minus qb, okay, which is nothing but the I mean the volume integral of this particular charge density, bound volume charge density, and that particular is given by del dot p. What is really important, what is that is uh, I mean, rho ps is equal to p dot a n hat. This is really very important expression. And one more is rho pb is equal to minus del dot p. Okay. Now, what very interesting, if you really remember, when we were discussing about the module 1, we said that del dot d equal to rho v. Okay. So we have kind of similar thing, okay, but this rho v was a free charge, okay, and here we have a bound charge, okay, and the volume bound charge is given by a kind of same expression, but we have a field called as polarization field, p field, del dot p, okay. And if you want really a surface charge density, really we can do this, d dot ds is equal to rho s, okay. But here, if you want a bound surface charge density, it is actually like P dot A n hat or P dot ds. Okay, that's what we have this. Okay, so now we'll try to get the more appropriate relationship. Let us consider dielectric region contains free charge. Okay, so now I'm telling you this is free charge. Okay, this is free charge someone deliberately has induced inside this dielectric. We sprinkle it. Okay, if rho v is the volume charge density of the free charge. Okay, when I say free charge, they are free to move. Okay, as like an electrons. the total volume charge density now inside the dielectric is rho v plus rho v pv. Okay, this is due to the bound and this is due to the free. So, well, we know that the point form of Gauss law, we'll try to apply Gauss law in a point form to a total charge, and we know it is del dot D equal to rho v, and we know that D is epsilon naught times E, okay, but now it is total volume charge densities, that is rho v plus rho v PV, okay. So let us solve for rho v. Rho v is del dot epsilon times E minus rho PV. Okay. So we know what is rho PV. It is del dot P minus or minus will be plus. So we can write in total del dot epsilon E times E plus P. Okay. So now you could see that we can really write this term as D in a more general form. So hence, inside a dielectric material, we can write expression for D is equal to epsilon times E plus P. P is the polarization of the dielectric material. D in more general form. So we know that in free space, okay, in free space, okay, in free space is a space where we don't have any matter, okay, so no polarization. So P is equal to 0, and you'll get back the same result, T equal to epsilon times E. Okay, so now, okay, so we got this relationship now. It is D is equal to epsilon E times epsilon E plus P. Okay. The application of E to dielectric material causes the flux density to be greater than it would be in the free space. Okay. So now, further we say that the relationship between E and P, okay, depends upon the type of the material we use. For an isotropic material, E and P are linearly related, and that linear relationship is given as equal to P is equal to chi. This is Greek letter, okay, which is pronounced as chi. Chi E epsilon times E, okay. But chi E is a dimensionless quantity called as electric susceptibility of the material. So making substitution this over there, we now write it as P is equal to chi times epsilon times E. Okay, so you can take some common, and you could see now I can write D equal to chi times chi E plus 1 epsilon naught times E. Now we call this term as epsilon R, okay, and that is a dimensionless quantity. It is known as the relative permittivity or dielectric constant of the material, okay, epsilon R. And hence we could write now the relationship between D and E is equal to epsilon naught times epsilon R times E, epsilon times E, okay. So this is how we get this relationship, and what is really very important, we made one statement, that is for an isotropic, that is linear homogeneous isotropic material, this is the relationship between P and E, and hence this is the relationship between D and E. Okay. So these are quite important things to really worth to remember. Okay. Yeah. So we know epsilon R and chi are dimensionless quantity, where epsilon is a dimension quantity. That is, it is not a dimensionless, and its dimension is per day per. I mean, its unit is per day per meter, as we know that epsilon is an absolute permittivity or a permittivity of the medium. Okay, so there are some nice note. Okay. First thing is that chi is, is a measure of how susceptible, that is how sensitive a given dielectric is to electric field. Okay, and for a free space and non-dielectric materials such as metals, the relative permittivity is 1. Okay, a material is said to be linear. Okay, a material dielectric is said to be linear if D varies linearly with the E. Okay, or we say that P and E are linearly related. Okay, a material for which epsilon does not vary in a region, okay, and it is same at all the points, we say that the material is homogeneous material. Okay, a material for which D and E are in the same direction, okay, or we say that E and P are always parallel regardless of the orientation of the field, okay, then we say that it is an isotropic material. Okay, so this is quite important because we often use this term, that is the material which we are considering. Okay, I mean in our syllabus we are going to consider only linear, okay, isotropic, homogeneous medium. Okay, and we should know what is it mean to be this. When I say linear, that is the relationship between P and E, or D and E are linear. When I say isotropic, the value of this epsilon is same at all the points. And when I say like an isotropic, okay, it means that yeah, when I say it is really an isotropic, E and P and D and E are in the same direction. Okay, same direction regardless the orientation of the field applied. Okay, yeah. So now we got to know how we have, I mean, how we got this relationship of D and E. Okay, and what happens when an electric field is applied to a dielectric material. Okay, and yeah, before we leave this particular thing, what I want to say is, for an anisotropic material, okay, cannot be described by a simple relationship that is D equal to epsilon times E. Okay, in that case, each component of this field is a function of each all the components of the E. Okay, and this is how they are related with the matrix relationship for an isotropic material. Okay, but this relationship, that is D is equal to epsilon E plus P, is really holds true for isotropic or non-isotropic. Okay, the only debates that I mean yeah, I mean only it debates for non-isotropic is that we cannot write straightforward epsilon times E. Okay, that's how it is related with the matrix or the set of equations. Okay. Yeah, but anyway, we are not going to study about non-isotropic material. Now, one more thing, what I want to say is, the theory of dielectric we have discussed so far assumes to be an ideal dielectric. Okay, practically speaking, no dielectrics are ideal. Now, what I mean this is, when electric field in dielectric is sufficiently large, it begins to pull electrons completely out of the molecules and dielectric becomes conducting. Okay. Dielectric breakdown or conducting. Dielectric breakdown is said to have occurred when dielectric becomes conductive. Okay. If you really apply that strong electric field, it's possible that these bond charges will, I mean, they are pulled out and they are start making conducting. Okay, and there where we speaks for given material, we also try to specify with an dielectric strength. It's a maximum electric field that dielectric can tolerate or withstand without electric breakdown. Okay, without electric breakdown. So for example, glass, you could say that it has an relative permittivity, yeah, sorry, um, okay, yeah, the relative permittivity is 5 to 10, and it has the dielectric strength as this much. Okay. Anything beyond this, there is possible of a breakdown. Okay. Okay. And you could see the you see a lightning phenomena. Okay, and that is because of this reason itself. Okay, the electric field strength is really so large. Okay, and there is a breakdown, and it's possible of conduction. Okay, yeah. So in summary, what I could want to say is D is equal to epsilon times E for dielectric material, and epsilon is given like this. Now, what is quite really interesting, you will see that del dot D is equal to rho V, and this rho V, what we is still is a free charge. This is a really very important. Okay, it's a very um, I could really mark this like a 5-star point to note down. Okay, so del dot D, whenever we write rho V, it still implies it's is only free charge. And similarly, D dot ds is equal to Q, and this is actually a free charge. And that's what we have said here. Okay. You could say that by even solving this, okay, we wrote this rho V equal to del dot D, and that this rho V is actually due to free charge itself. Okay, it's not due to any bound charge and all those things. Okay, I think this is the topic I want to discuss, and in order to make this topic a little more concrete, I really prefer to solve few problems based on this. Okay, so quickly, let's see what the problem is. The electric field intensity in a polystyrene having an relative permittivity as 2.55, filling the space between the plates. Okay, that is, you have two conducting plates, that is like a capacitor, and the dielectric material is polystyrene. Okay, parallel plate capacitor, and is known to have an electric field 10 kilovolt per meter. Okay, the distance between the plate is 1.55 millimeter. Calculate D, okay, calculate P, polarization, and calculate surface charge density, free charge density on the plate, and also try to calculate the surface charge density of polarization charge and potential difference between the plates. Okay, so quickly we can do this D, because now we know what is D and E. They have given E, and D and E relationship is known to us due to dielectric material, so you can really compute that. We know that P and E also related by chi times epsilon naught times E, and we know what is the relationship between epsilon r and chi, epsilon r equal to 1 plus chi. So we can write chi as epsilon r minus 1, and we can solve for the polarization. Okay, now what is free charge densities? Okay, this is quite simple. Okay, as I said that we know that D dot A n hat leads to an free charge density. Okay, because we know that del dot D leads to a free charge volume charge density, then similarly D dot A n hat, okay, should leads to an surface charge, free surface charge densities. That's what we have. Okay, so D dot A n hat. So if you want to find polarized charge density, okay, it's given by P dot A n hat. Okay, as we have discussed very recently. Okay, then there was B equal to E. They asked what's the potential difference. Okay, you could see that the electric field is really uniform. Okay, and as I said that if it is really uniform, we know E equal to V equal to E into L, or L is nothing but like a D, so V equal to E into D. Okay, because I should recall you that E dot dl. Okay, if E is uniform, it is simply like L. That's what we have, E be equal to E into D. Okay, so you can substitute what is E and D, and that's what is 50 volts. Okay, so this is what is something quite interesting. Okay, so if you want to find a free charge densities, you can use D, and if you want to find what we say is bound charge densities, you can use the polarization. Okay, a dielectric sphere, it's a dielectric sphere with epsilon r as 5.7 of radius 10 centimeter, has a point charge of 2 picocoulomb placed at the and placed at its center. So you have a dielectric material, okay, and at the center of that they have placed the 2 picocoulomb, okay, and now this 2 picocoulomb is actually a free charge. Okay, so this is actually very interesting. You should really recall this. I mean, remember, I mean, make a note of this one. This 2 picocoulomb which is placed is actually free charge. Okay, at its center. Calculate surface charge density of a polarization on the surface of the sphere. Okay, see, because of this free charge is present, okay, this material will get polarized. Okay, so we said that we have a dielectric material. When we apply an electric field, it gets polarized. Okay, and this electric field must be because of some source, is it not? And in this problem, this 2 picocoulomb which is placed at the center is itself the source, okay, which makes this material polarized. And because of this material is polarized, it has now bound surface charge densities. And we need to calculate it. And in order to calculate bound charge densities, we need a polarization. And we also know that E and P are related. Okay, so first I can really find electric field due to this free charge, which is Q divided by 4 pi epsilon r square AR hat. Okay, and from there I can find P with this relationship. Uh, P and E are related. Okay, as that what we have. Okay, and then you can find this surface polarized charge surface charge density P dot A n hat. Okay, and I think it's quite simple. You can go to that a simple substitution. And this an hat, okay, is nothing but the unit vector outward normal to the surface. This is we have taken a sphere, and for that we have like an ar hat. So it is p dot ar hat. So you have here p, and here we got to know what is rho ps. Okay, so that's quite simple. And next you need to find the force between this 2 picocoulomb and the 4 nanocoulomb which is placed on the surface of the sphere, and that we can do it using the Coulomb's law. Okay, that's good. Then I think this is quite a similar kind of problem. I think you can really go through this one. Okay, I have written in quite detail. Okay, and you could see that after this, I mean, we have discussed about the boundary conditions. Okay, and as I told you that boundary conditions will help us, okay, to find and field if you know the field in one region. Okay, now what is I really mean by boundary condition? Okay, so you have you have two regions. In one region, okay, you have a dielectric material with epsilon r, say 2, and in one more region you have a dielectric material, okay, with epsilon r equal to say something 4 and something. Okay, you know what is electric field and D field in one region, and you are interested to find here. Okay, and in that case we use a boundary condition. And we know what is really a boundary condition between between two dielectric material, and we know what is the boundary conditions between dielectric and conductor, and free space and conductor. Okay, so you should really remember those boundary conditions which will help us. So I have taken one problem on the boundary condition between two dielectric material. So here I have region 1, okay, which is a free space, okay, where they have given the electric field as E equal to E naught times AX hat and D equal to epsilon times E. Okay, and there is no polarization in free space. Here also we have free space, and here I have a region that is having a dielectric material, okay, that is Teflon with a epsilon r as 2.1 and chi I is 1.1. And now the question is, I need to find an electric field, D field and P inside this polarization, inside this Teflon. Okay. Now I'll try to use my boundary condition between two dielectric materials, that is free space and dielectric material. Okay. And I know that the boundary condition between two dielectric material is, that tangential component of electric fields are same. That's what I have written here. Tangential components are same and normal components of D fields are same. So this is the things which we have to remember. Okay, the tangential component of E fields are same, normal components of D fields are same. Okay, so with that, the same thing, we are going to find the fields in the other thing. Okay, so we know what is D1 is given here. Okay, which is epsilon naught E naught AX hat. Okay, and you could see that as dn1 is epsilon naught E naught. Okay, and inside this Teflon 2, okay, I can say that dn2 should be equal to epsilon times E2. Okay, I'm saying that here it is, here the field is D2 and E2. So dn2 should be epsilon times E2. Okay, and as I said, dn1 should be equal to dn2. So dn1 is epsilon times E1. It means that dn2 should be also equal to epsilon times E naught. Okay. Yeah. Yeah. So we can really equate these two now. Okay. So from there, I can really solve for E2. And you could see E2 is by making all those substitutions. Okay, as epsilon is nothing but epsilon naught times epsilon r, epsilon get cancelled, E naught by epsilon r, E naught by 2.1. And I got to know what is E2. Okay, yeah, and before that I say that the dn1 is equal to epsilon E naught because this itself is a normal component. Okay, so this is because x equal to 0, x equal to a. Okay, so this itself is a normal component. What D field they have given to us is itself a normal component. Okay, so with that I got to know what is E2. Okay, so once you know what is E2, you can really find D2. That's not a big deal. Okay, so the question was to find P now. Okay, and we know that inside that dielectric material we can write the relationship for D as epsilon naught times E plus P. I can solve for P. P is D minus epsilon naught times E. I know what is E now. Okay. Okay, next you can make those substitutions and you can solve for P2. Okay, so in the region 2 inside a Teflon, I can find my D2 is this much, my E2 is this much, and my P2 is this much. Okay, so this is actually quite simple. All the thing is that you should try to identify, you should try to remember the boundary conditions, and from there you can really try to solve it. Okay, so this is really a practice problem. Okay, with above discussion you can really solve this problem. Okay, so here I really complete. I tried my maximum. I tried maximum to cover up all the concepts really which is essential. Okay, and which are not part of a syllabus. I have really tried to cover with the greater details, and I also have solved a problem so that it becomes, so the concept becomes strong. Okay, so that so that it's useful to use. Okay, when we go to the module 4 and module 5. Okay, so with this we'll try to conclude today's class. Thank you.